Good morning, OffensiveCon. It's been a long time, hasn't it, since probably many of us have actually been able to attend an actual conference in person. It seems pretty crazy. So yeah, I'm James. I work at Google in the Project Zero team. And the title of my talk is a pun on a quote which apocryphally comes from Groucho Marx, and apparently it wasn't really him. But I'm actually going to be talking about the relaying of Kerberos authentication. Probably sounds a very dry topic. But I do have a blog post about this research as well, which goes into actually quite a lot of depth about some of the sort of network protocols that I'm going to be talking about. But I thought what would actually be quite useful for people to fully understand the impact of my research is to run demo exploitation scenarios. And maybe you can take some of that away and actually use that in your own sort of client engagements or red teaming and things like that. So I don't want to embarrass anybody by asking like who doesn't know what NTLM authentication is, or NTLM authentication relay specifically. NTLM itself is a network authentication protocol introduced in the original versions of Windows NT, kind of clues in the name. And the idea being an authentication protocol allows two computers in a network to authenticate to each other, but in general, one of its useful properties is that if an on-path attacker can sniff the traffic, they can't necessarily derive your password or some important secret. It's kind of sort of obfuscating the authentication. Unfortunately, NTLM was designed in such a way that it had many, many security issues, or design flaws, basically. And one of the most egregious is the ability to be relayed. So NTLM originally never specified the target of its authentication. So it didn't matter whether you were authenticating to one server or a different server. Effectively, the authentication protocol worked pretty much exactly the same. And this could result in something called a relay attack, where an attacker could the attacker could induce a network client to connect to their own server, and then say, hey, client, could you just authenticate to me with your user credentials, which of course isn't your password, but is some sort of specialist protocol to do this. And because there's then no sort of targeting for that authentication, the attacker can then just forward that authentication traffic to a service they want to try and compromise. And so you could forward it to, say, a really important service on the network, and you could then impersonate that authenticating user on that service. And from that, you can compromise the whole network, potentially. And there's tooling to do this. Like, you don't actually have to write your own NTLM relay stuff. If you get the Impacket Python library, for example, there's an example, NTLM Relay X. And it pretty much works out the box. It allows you to relay between different network protocols, say between HTTP and SMB and vice versa. And it just sort of works, and it's great. Now, last year, there was actually some very interesting research which came out of SpectreOps, specifically by Will Schroeder and Lee Christensen, talking about Active Directory Certificate Services. And Active Directory Certificate Services is a service you can deploy on your Windows domain, which allows you to effectively act as a certificate authority. And you can actually have a web server which will issue certificates for user authentication. So if a user goes to this website, they can say, please generate me a certificate, an X509 certificate, and you can then use that certificate in place of your normal user authentication credentials. So without knowing the user's password, you could actually compromise it. And it turns out that this web server, by default, was vulnerable to NTLM relay. So of course, if you could relay an important user, say a domain controller, to the Active Directory Certificate Service web server, you could get a certificate to pretend to be that domain controller anywhere on the network. And that's usually considered a bad thing. Now, it's surprising the number of correlations with Mark's keynote about the sort of types of issues that you find in these sort of scenarios. One of them is that legacy technologies, legacy complexity is generally a potential security risk. And Microsoft are renowned for their backwards compatibility. So they really, really don't want to break existing users of theirs technologies. So they've bolted on stuff to NTLM over the years, things like this extended protection for authentication, but it's not on by default. You have to actively turn it on. Now, as far as I can tell, I've not found a way of bypassing extended protection for authentication, certainly not in this research. But one of the other mitigations that Microsoft suggested was just to disable NTLM. Like, NTLM is a deprecated technology. It's been around for 20 plus years. Maybe it's about time we finally retire it and just turn it off in your domain. Now, of course, most actual Windows domains probably can't do that for, again, backwards compatibility and legacy reasons. But it is still an option. But what particularly got my interest is if you sort of dig through the links, it does specifically state that you should turn off NTLM because you should really be using more secure authentication protocols like Kerberos version 5. And this makes perfect sense. Kerberos version 5 was introduced in Windows 2000, which, again, is over 20 years ago. And it is supposedly more secure. So why wouldn't you want to disable NTLM and rely on the more secure authentication protocol for your Windows domain? But that got me thinking, well, if NTLM is relayable, what is actually stopping you relaying Kerberos? Is there actually some fundamental principle which makes it completely relayable? And this has basically formed the foundation of my research. So I do not have the time to go into the minutiae of Kerberos and the very many ways in which it can be used and abused. So I'm going to focus specifically on this sort of relay scenario. And the way in which relay is protected against in Kerberos is using something called a service principal name. Now, service principal name, usually when you see it as a user, is just kind of a text string. But it consists of 3 components. The first component is the service class. This indicates to the authentication process what type of network protocol you're trying to communicate on. So host, for example, is just like, I'm generally trying to talk to a computer in the Windows domain. There could be HTTP, which is for web servers. You could have CIFS, which is for SMB, which is the Common Internet File System. So this allows you to sort of potentially limit, like when you're trying to do authentication, this could be potentially checked to say, oh, well, I'm an SMB server, but they've said I want to use HTTP. So in theory, this should block against sort of cross-protocol attacks. Now, the second component of the service principal name is usually referred to as the instance name, and at least in Microsoft environments, this is configured to be the name of the computer account or the domain name of the computer account, which is associated with the SPN. So at the bottom, we've got sort of a bit of PowerShell. You can query like the Active Directory LDAP server and say, for a particular computer user account, give me all its registered service principal names. The final component is the service name, and this is just allows the option to differentiate between different applications on the same server with the same service class. Now, in general, you don't see this used very often. It's very, very rare that you see it used. And as you can see in the list of service principal names, there is actually none of them which register a specific app type. So what is that service principal name actually doing to prevent the relay? Well, let's assume that we are in our sort of classic relay scenario. We have an evil host, an attacker, sitting on our network and is inducing a network client on a workstation to connect to it and saying, hey, can you authenticate to me, please, so I can just do some funky thing that you want me to do instead of actually stealing your authentication credentials and compromising your network. At that point, the workstation is going to go, okay, I will ask my local security authority, the LSA process, hey, I need to authenticate to this server, and this is the SPN, the service principal name, I believe it should be on. And in this case, we're going to evil host. So as I've shown with the previous slide, well, presumably you'd put evil host as the instance name. That SPN is sent to the Kerberos server on the domain controller, and what it will do is it will take the user's authentication details, package it up in something called a Kerberos ticket, or a service ticket, and encrypt that service ticket using a key which is only known between the computer account, which in this case would be evil host, and the domain controller. Now, when that Kerberos ticket is sent to evil host, it can decrypt it because it knows the key. However, crucially, from a relay perspective, if you were to relay that Kerberos ticket onwards to a completely unrelated server, the keys should not match. Of course, like if I know server's encryption key, you've already compromised server. You don't really probably have to do very much else. But in general, by having these differentiating keys, you can't just forward the ticket on. So basically, the fundamental challenge here is, in order to sort of exploit this scenario, you're going to want to somehow have an SPN which doesn't match with the actual network address that it gets connected to. So I did at least search for sort of pre-existing work in this area. There is a tool called KERB-RelayX. That sounds awfully familiar. It sounds like NTLM RelayX. Presumably, it's doing the same thing. Unfortunately, this is only abusing another feature of Kerberos called unconstrained delegation. And so it only works in very specific scenarios, and it doesn't work, crucially, in the general purpose. I've got an untrusted box sitting on my network, which is basically relaying authentication traffic to some other privileged server on the network. So I needed to do some research. And of course, there's a lot of potential network protocols which could use Kerberos authentication in a Windows environment. So I did that research, basically. That's all you can do. So specifically, in order to fully understand how Kerberos is used in a Windows sort of network protocol, you kind of have to also understand what the API set is. And the API set, in general, is you use something called the Security Support Provider Interface, or SSPI. This is a set of APIs provided by Windows which will talk to the local security authority and perform authentication. And it's designed in such a way as to be effectively like opaque. You don't necessarily have to know what authentication scheme you're using. You just follow a set of basic rules, and you can perform any type of authentication. But the basic principle is, on the client, you set up some sort of authentication session, and then you run just like an iterative loop. And you sort of say, get me the next authentication token, which is just like a binary blob, at least from the client's perspective, although, of course, it has some sort of structure. And the client can then pass that opaque blob across to the server, which has a corresponding iterative loop, which is sort of accepting these authentication tokens. And that process may generate a token which it then sends back to the client, and so on and so forth. And eventually, the iteration either fails, your authentication fails completely, or you've succeeded, and both sides are sort of like going, yep, we're all authenticated, we're all good. Let's carry on. So some of my work was, of course, doing reverse engineering, but of course, this also applies if you're doing the source code review. There's a bit of source code review, and you want to know what these APIs actually are, so that you can just search for them in the code base and go, right, okay, this is where Windows authentication is happening. So the first function is the acquire credentials handle function. This is basically setting up that authentication session for you. The thing of most importance here is the package name. And this is like a text string which indicates the type of authentication you want to use. So of course you've got NTLM, which is just pure NTLM, nothing else. You have Kerberos, which is just pure Kerberos and nothing else. And then you have negotiate. And negotiate is a mechanism to basically choose the best available authentication scheme between the client and the server. And in fact, this is the one you're most likely to see used on a Windows network, because it means that if NTLM is the only thing available, NTLM will be used. But of course, if Kerberos is available, that potentially will be used in preference to the more insecure NTLM. Now, on the client side, you then call this initialize security context function and pass it this sort of handle to the credentials. The key parameter here for our discussion is the target name, which for Kerberos authentication is, of course, set to the SPN that we want to use, which effectively identifies the key, which will encrypt the ticket for us. If you don't specify a target name at all, then of course Kerberos will just fail, or negotiate will only ever try and use NTLM, assuming it's not actually disabled in your network. The next parameter you're going to be interested in is the context request parameter. These are a set of flags which indicate the types of features you want in your authentication protocol. Now, one of the ways of mitigating NTLM relay attacks is to use signing and encryption. And the way this works is when you do the authentication, a session key is negotiated as part of that authentication process. And that is in some ways protected by the shared key or the shared secret between machines. And so an on-path attacker can't know that information. So if if signing or encryption are enforced, then of course the relaying attacker can't actually relay that traffic without the server just rejecting that actual protocol. You've then got input and output buffers. This is for sending in and out the authentication tokens. There's also some interesting quirks. If you look at the Project Zero issue tracker, you'll find some interesting stuff in there as well. Now, one thing to note about these flags is that when you use negotiate, negotiate has a requirement for integrity checking. And so what it does is it will actually set the integrity flag automatically for you. So no matter what the client is setting for these flags, integrity will always be enforced in negotiate. But we'll see an example where that isn't always the case. Now on the server side, you may think you just need to look at the client, but it's also worth looking at the server as to what exactly it's doing with that information, because this feeds into what services can I relay authentication traffic to as well, because not all, they may do some additional protections based on the authentication. And probably the main thing you're interested in here is that there's an output parameter containing the flags negotiated as part of the authentication process. And so this will reflect the client asks for integrity checking, the client asks for encryption. And certain services like LDAP can use this as a way of opportunistically enabling anti-relay protections. They can go, well, the client supports signing, so I'm going to turn on LDAP signing so that if someone is relaying this traffic, then you can't obviously attack it. That's the theory. Okay, so obviously once you've identified that, then of course you can go into the protocol research itself. And I'll start with RPC protocols. And as I said before, there is a blog post with more different protocols in it, some of them better than others. But I decided to choose the ones which were probably the most useful and also the most interesting to demonstrate. So Microsoft, or Windows, comes with its own RPC library, as I'm sure most people are aware. And you can do, obviously, Windows authentication. It makes perfect sense that you can do Windows authentication on RPC channels. And in the client, if it's doing authentication, then you will see a call like this, RPC binding set auth info. And it has 3 parameters which are particularly interesting. The first one is server principal name. This is the service principal name. For some reason, it calls the server principal name for RPC. I have no idea why. And this is just your SPN, if you want to use Kerberos authentication. Now, if you don't specify one, and crucially, you are enabling negotiate authentication, then it will generate one automatically using this pattern of restricted Kerb host and then the host name. But the client could set one to an arbitrary value. The next parameter of interest is the authentication level, and this is usually what identifies what sort of anti-relay protections you're going to end up with. If the client is using the connect level, then no integrity checking, no encryption is enabled, and usually you can relay to that server without any problems. However, if integrity or packet privacy are turned on, then encryption and signing will be there on. And of course, it will add the corresponding flags to the authentication process so that if that RPC client connects to you, it may limit where you can relay that traffic to. And then the final parameter is just you can select your specific authentication protocol. Like WinNT is actually just NTLM, and you then got negotiate and then raw Kerberos. So on the server side, there's a function which looks awfully similar. But if you kind of remember back with the accept security context function, you'll notice that there was never a parameter to specify the SPN you were expecting in your authentication process. So why would you want to specify a service principal name on your server? Well, one option is once the authentication is completed, the server can actually query for the SPN the client used and just say, hey, does this match my expectations? And if it doesn't, if it subverts its expectations, it could, of course, just tell you to go away, basically. And the other one is, of course, I need to specify my authentication service. What do I actually accept? It just turns out, though, that that SPN isn't actually used for verifying whether the client set the right SPN or not. Instead, it's used for this function. So this function is a RPC management function, and when your RPC server starts up, it creates like a hidden RPC interface. And one of the calls on that RPC interface is, hey, tell me what the server thinks its SPN should be. And you might notice an obvious problem here. Like, if the client says, hey, server, what's your SPN? Well, the malicious server could go, well, it's this domain controller. Could you just generate my Kerberos authentication for me for my domain controller? Thank you. And just pass it back to me. And of course, at this point, we've now got a potential decoupling between the host name that we connected to for your RPC channel and the SPN that we're using for that Kerberos authentication. And at that point, relay is potentially possible. Unfortunately, I couldn't actually find many clients which use this function. This isn't something which is done automatically for you. You have to explicitly call it. And so I never found a particularly good RPC client to use it. However, like raw RPC clients aren't like the only thing which uses RPC on Windows. Now, anybody who knows who I am probably knows I have a bit of a thing for COM. I'm a bit weird like that. But when you're trying to send objects between processes, COM processes or COM servers, all the information necessary to connect to that server, to that original object, is wrapped up in a special obsref structure. And it contains things like the object exporter ID, which is kind of like a unique identifier for which server exposed that object to me. But it also contains RPC binding information. And this is actually two parts. The first part is the string binding, and this is used to generate the actual connection to the RPC server. So it basically says, connect over, say, the TCP RPC protocol to this hostname, please. This is where the object lives. But interestingly, that's like a perfect demonstration of a decoupling between where you're connecting to and where the security lives, because the second part is the security binding. And the security binding contains, what authentication protocol do I want? So I could go, I want Kerberos, please, just raw Kerberos. And this is my SPN. This is my service principal name that I'm I'm going to do. So of course, a malicious COM server can say that's anything it likes. So the basic attack is something like this. Now, in general, this is easiest to do on a local system rather than between servers because of the way of COM security generally works. Only sort of relies on administrators and things like that, which is pretty awkward to deal with. But the attack basically revolves around, you have your malicious process, sets up a COM server, and registers its RPC binding information in an obsref with the local octid resolver inside the RPC subsystem. The attacker can then marshal a COM object using that obsref information to some sort of privileged service on the local machine. That will then unmarshal it, which causes the COM runtime to try and look up the binding information for that object from RPCSS. It will then try and connect back to our attacker, and of course we've just stuck whatever SPN we like and whatever authentication protocol we like, and we can now forward that traffic on to some arbitrary service somewhere, either potentially locally on the same machine or remotely to a different machine. So you can do this fairly easily without actually having to write any custom RPC protocol parsers or anything like that. It's called co-initialized security. Set an arbitrary SPN, and nothing ever bothers to check. So what can you do with that? Well, one attack which Elad Shamir discussed in his pretty amazing blog post called Wagging the Dog is abusing resource-based constrained delegation in a domain environment. And this basically allows you to do local privilege escalation on a domain join system, as long as, crucially, LDAP signing has not been enabled. So, as I'm sure everyone is particularly interested in seeing, we'll go for a demo. So, I have an environment set up which is, if I can, oops. Not sure how to increase this. Can people see that? Is it okay? Yeah. All right. I can't work out how to increase this font without a scroll wheel, unfortunately. So I've got a simple domain environment set up, and I've got some scripts. So in this demo, I've got like a very simple script called so exploit computer account. And this runs, creates a new computer account, runs my tooling to do the decom relay, and then uses the Rubyist tooler. Possibly some of you have used that to perform like a service for user attack, which will get me a Kerberos ticket for the domain administrator on my system. So obviously, hopefully the demo gods will like me today. Okay, so it looks awesome, right? Like obviously, everyone knows that once another console window pops up that you've completed the exploit. Unfortunately, if I look at that, I'm still domain Alice user, so it's not that interesting. However, if I look at my Kerberos ticket cache, I have now a Kerberos ticket for the domain administrator for my local machine. And now I can basically connect to the local SCM, use Kerberos authentication as a domain administrator in the local machine, and hopefully, I now get a second one pop up, which is a bit more privileged. So, okay, so another protocol of particular interest is HTTP. As I said before, with the Active Directory Certificate Services, which using HTTP is a pretty sort of simple authentication protocol that it uses for Windows authentication. You make your request from your HTTP client, and if the server wants you to do Windows authentication, it returns you status code 401, unauthorized, and says in a www authenticate header, hey, use negotiate. And this could be like basic authentication or digest authentication, but in this case, we want negotiate authentication, please. And so the client can then kick off its Windows authentication loop using the SSPI, and it generates an authentication token, converts that into base64, slaps it in an authorization header, sends it back to the server. And of course, this can go on for multiple hops, depending on how many trips around that iteration loop you need to go. But eventually, hopefully, the idea is that you authenticate to the server. And again, as Mark was saying, reading protocol documentation isn't necessarily a good idea, because if you read the RFC, and no one should ever believe that anyone implements anything to the RFC, it specifically states that if you're using Kerberos, you should probably use a principal name in the form http/hostname. Okay, great. So that would probably seem to eliminate the possibility of any useful attacks. Because again, as I pointed out, you need to decouple the server you connect to from the SPN that is used. But of course, what does the implementations actually do? It's not what the RFC says, it's what the implementations do. And the first one I looked at, WinINet, is pretty much the progenitor of the negotiate authentication scheme for HTTP, because WinINet is the core networking code for Internet Explorer. And strangely enough, a few other things as well, as we'll hopefully see later. And what it does is it calls this generate fully qualified domain name and SPN function. It first looks up the fully qualified domain name of your URL. So this is if you pass it an undotted name, it will try and put the domain suffix at the end of it. And then if there's a special flag, this global use CNAME for SPN, it will just use that as part of your SPN. However, in general, this is not turned on. This is an optional feature that you can turn on. So instead, it calls get canonical name. and then it returns that. But the ultimate end result of this is one of those two strings ends up being stuffed into the SPN with a HTTP service class. Okay? That doesn't sound particularly strange. So where is those values coming from? They're coming from DNS. Like, when you make the connection to the web server, it's going to look up the host name using DNS. And as part of that, it specifies two flags. It says, return me the fully qualified domain name and return me the canonical name, please. And as part of the address record, should be these two strings, which you can then store for later use. And it'll also store the address to connect to. So of course, it's making a connection to the server and storing away the information about that DNS lookup. So again, doesn't sound particularly that useful because of course, it's just doing a DNS lookup, right? But where's that canonical name coming from? Well, the canonical name comes from the DNS address record itself. So it's not like, with a name like CNAME, you'd think it'd be like the CNAME record if you know anything about sort of what DNS records are. But it's not. It's actually coming from the address record itself. Specifically, the address record says, I'm on 10.0.0.10, which is the address of the domain controller, but my name is primarydc.domain.local. Okay, so that's our canonical name. That's the address we get. Now, you may think, okay, can I just spoof that? Like, I can do a recursive lookup to my random my random DNS server somewhere on the internet, and I can return some arbitrary address record which spoofs that name. Unfortunately, it doesn't tend to work because, at least on the Microsoft DNS server, it does do some checking that if it's doing a recursive query, that the address record looks like it's valid, looks like it's not being spoofed. Because, of course, if you can spoof DNS, you can do all manner of fun stuff. But it turns out that there is a way of doing this. On a typical Windows installation, like a default Windows installation, it enables this linked local multicast name resolution protocol, which I'm sure if you've done any NTLM relaying, you may already have heard about. But unlike that, where you're generally trying to get someone to connect to you and pretend you're actually an existing server, the idea here is you just say, actually, I'm evil host. Connect to evil host, please. And because LLMNR bypasses the DNS server and goes straight to the DNS resolver in the client, we can actually decouple the address from the canonical name. We can set it an address which is not my domain controller and is actually my attacker's machine, but send it actually, but I'm also primarydc.domain.local. And you've got that decoupling. So a simple example of that spoofing is, of course, you set up your machine running a simple LLMNR. There's tools like Python Responder, for example, already do a lot of this for you, but don't do this specific attack. The WinINET client will, of course, try and resolve evil host, and it will connect to our web server on evil host. We return a 401 response, but at this point, it's already pulled out the canonical name, which you've set to file server. And so it builds an SPN using HTTP/file server, not HTTP/evil host. And of course, at that point, we've got effective authentication between the computer and file server, so we can just relay it. And we perform our attack that way. Okay, so that's WinINET. So you'd think, okay, it's quite old code. Clearly something like Chromium is going to do a better job, right? So you look at the implementation in Chromium, and interestingly, you look at the comments in the Chromium source code, and it says, we're doing this because we're trying to emulate Internet Explorer's behavior. It turns out they don't implement Internet Explorer's behavior, or at least they do, but ironically, because of course Internet Explorer is closed source, the Chromium developers don't necessarily know how Internet Explorer did it, so they just did it how they thought they did it. And what it does is it does a second DNS lookup. And you could probably even see where this is going at this point, right? Now, there is a way of disabling this, an option to disable this behavior, but of course, that's never turned on by default, right? And so it does the DNS request, and it gets back the result, and it pulls out the canonical name, and it builds the SPN based on that canonical name from DNS. You think, okay, that's great and all. Well, you can, of course, change the response from the DNS server, because, of course, the DNS, it has to do one DNS request to talk to your web server, and then do another DNS request to actually generate the canonical name. Now, of course, in general, your DNS record will have a long TTL, which means it will be in the DNS cache, so it won't actually do a second DNS request. But there's nothing stopping us returning a TTL of like 1 or 0 and immediately purge that entry from the cache. And then when the second DNS request goes on, it actually does something useful. Now, of course, there is a slight complication here. In order to get Chromium to automatically authenticate, you need to provide it with an intranet zone URL. And in general, what that means is you need to provide it a name with no dots in it. So of course, if you connect to evil NS or evil host, it will try and do automatic authentication on the local network. However, if you gave it evilhost.domain.local, then it's not going to do automatic authentication. So we need some way of adding a record to the local DNS server which allows us to abuse this. And it just so happens that, at least by default, any user, any authenticated user on a domain can write their own DNS records to the Windows domain server via LDAP. Unfortunately, the complication lies here in that the LDAP approach takes sort of 60 to 90 seconds before it refreshes. So it's not something we can't race a window of like a second between the initial request for connection and the actual lookup process. However, instead, what we can do is, instead of writing an address record, we write a delegation record or a name server record. And what this does is it allows us to route a name lookup to an arbitrary DNS server we can control. And yes, there was already our problem that we can't return arbitrary data, but fortunately, there's a way around that. So when Chromium now connects to evil NS, domain.local, of course, we return it back an address record for our malicious server. Pretty easy. Return a 401 response. Chromium goes, right, okay, I now need to do authentication, so I'm going to do a second DNS lookup. By this point, our DNS record has expired. And it looks up again, and now instead of our DNS server returning an address record, it returns a CNAME record for the target SPN we want. So we return it, say, file server or primary DC. And what the Microsoft DNS server will then do is it will actually look up the actual address record for that server and return it. And Chromium will get back an address record which contains the real IP address of file server, but by this point it's too late. It's already connected to our malicious server. But instead, it will use only the canonical name from that record to make the SPN for the Kerberos authentication. And then, of course, we're back to the whole relaying trick, right? So a few more interesting things with HTTP. I wanted to be able to disable the integrity flag. Like pretty much every implementation always used negotiate. However, I noticed that a few implementations I looked at, specifically .NET, the .NET Framework and .NET Core, if you return Kerberos as your type, even though the RFC says you only use negotiate, or at best you use NTLM, for .NET Framework, if you return Kerberos, it will just use plain Kerberos, and that means you never get the integrity checking turned on. For .NET Core, there's an even funkier implementation trick. Even though it's not explicitly specified, there is actually an undocumented thing that when you call initialize security context, you can pass it an initial token. So even though Kerberos doesn't usually work like that, or negotiate doesn't tend to work like that, you can pass it an initial token. And if that initial token looks like a Kerberos token, and like literally it checks for 3 different bytes, if it looks like a Kerberos token, it goes, oh, this target is actually speaking Kerberos to me. So instead, what I'm going to do is just disable negotiate entirely and go straight to Kerberos. And again, that would disable integrity checking. Now, only .NET Core, as far as I was aware, actually uses that value and puts it straight into initialized security context. But it's still a kind of a funky thing. And you can do the same with NTLM as well. It's kind of fun. So the results of HTTP, because I tried to do a broad spectrum here, things like Firefox had the same sort of issues as Chromium. The key difference with Firefox is Firefox never enables Windows authentication by default anymore. Like, even with an undotted name, a default installation of Firefox will not do Windows authentication to an arbitrary server, which is good. But the ones I've highlighted, .NET Framework and .NET 5, are probably the most abusable HTTP clients out of the lot I looked at. And there's also the delegation column, and this is like, do we turn on the flag which enables Kerberos delegation? That will become important for something at the end. Interestingly, .NET 6, the code for .NET 6 is not that different from .NET 5, but you cannot disable integrity. And that's because the .NET 6 code base added that integrity flag to the SSPI call, because it was not because they thought, hey, we need to work around NTLM relay or anything like that. It was actually because the macOS implementation of NTLM was so broken that they needed to set this flag, otherwise it blew up. So it's all Apple's fault for breaking .NET 6. But anyway. So we can demo that. So in this particular case, I've got my my attacker box sitting there with my own custom LLMMR server on it, and that's running on 10.0.0.80, which will become important. So, and I've got just a simple web server on my domain controller, which just allows me to just basically print the authentication details that the user has provided. And the thing to bear in mind here is, of course, it tells you who connected to me. So in this case, I am on my client machine, so it's of course 10.0.0.102 is the one which connected. Now, in order to demonstrate WinINet, it's kind of difficult on Windows 11 because they've removed the front end for Internet Explorer. But actually, the actual back end for Internet Explorer is still there. And so what I've done here is I've turned on, if you see in the background, something's already tried to authenticate to my server. Like before I even typed evil host, it's already actually tried to make an authentication scheme to it. So I use Internet Explorer mode in Edge to actually host Internet Explorer inside Edge itself. But crucially here, we've fully authenticated using Kerberos, and we're actually coming from 10.0.0.80. So of course, we've managed to relay our traffic through my Linux box to the actual target server. We can also just run a simple HTTP request just to demonstrate the sort of .NET Framework stuff. I just clear that so you can see it. So HTTP request. We go to evil host, and then we give it just a parameter of, please use the Kerberos authentication protocol, please. And hopefully it goes back. And if you look on Edge or Internet Explorer, you see the integrity flag is set. But if we look at .NET Framework, in here, the integrity flag is not set. And so, again, this can now be much more relayable. So, I obviously looked at various different protocols, and one of them would be, hey, I really want to be able to relay from SMB, because SMB is like, just basically if you can find something which will open a file, arbitrary file path, then you can point it at a arbitrary SMB server and potentially steal it. And this is used for things like the Active Directory Certificate Service trick. There was a technique called Petit Potam, which used the ability to generate SMB traffic or potentially web dev traffic and relay the authentication scheme from that. Unfortunately, after much research into the SMB client on Windows, I just could not get something to work. There seems to be some weird behaviors, especially around things like distributed file system or DFS. But whatever I tried, I just could not get it to work. However, I did notice something weird when I was actually debugging this process. Now, if you look at the kernel client, you'll see a function literally called build SPN. And inside there, it calls this sec make SPN ex2 function. This is like the perfect Microsoft named function, right? It's not just an ex function, it's ex2, because it's even more improved. But you think, well, this is just basically a mechanism to concatenate a string together, so big deal, right? Setting the CFS service name, which is just CIFS for SMB, and it's setting the host name. Big deal, who cares? Well, if you actually look at what is returned by this API, it looks like that. Now that looks weird. That's the best way of putting it. It has at the front of that string what looks to be a normal SPN, then it has all this crap after it. And that seemed odd. And I thought, well, okay, maybe it's just some special kernel thing, right? Like, kernel's weird. It does some weird shit sometimes. But I actually plugged in that string into, like, the user mode SSPI interface, and it authenticated, generated Kerberos authentication for CIFS/file server. That's weird, right? I actually tracked it down eventually to code inside the local security authority process itself. Specifically, so this would work, this isn't specific to Kerberos, this works across basically any authentication protocol that it uses. It looks at the target name and then passes that target name to this cred unmarshal target info function. And what this does is it looks for that garbage at the end of the string is this marshal target info. And it's basically, it seems to me like someone in the development team decided to try and violate some layers, and they really didn't want to have to plumb in the code to get some piece of information from the SMB client to somewhere else in the system. So instead, what they did was they hacked LSA to basically create like a backdoor of a fashion. It's not really a backdoor. But if that data at the end of the string is a valid target info buffer, then it's going to subtract all of that from the target info, from the target name. And so you end up, once it gets to Kerberos, that garbage string has turned into the SPN you were expecting. And you may think, so what? Well, so what is, of course, that string is clearly file server with garbage at the end of it. From a DNS perspective, it's not the same as file server with no garbage at the end of it. And while I might not be able to compromise the DNS record for file server, I can almost certainly add a DNS record for file server with garbage at the end of it. So we can do a very quick demo of that. On my Linux box again, go away, thank you. On my Linux box, I've just got a SOCAT listener. It's listening on 3389, which is the RDP port, and then it's just forwarding on to server 2022 domain.local on its RPC port. So if I create remote desktop, if I try and connect to linux.domain.local, which is my Linux box, we can see traffic going through it. And just to be double check, we try and log in as an administrator. And it says an authentication error occurs. And the reason this is failing is, for the most part, because I've disabled NTLM on my network. So it will kind of work with NTLM, but because I've disabled NTLM, it just goes no. But we can see it has actually traversed our server, right? However, if I choose my nicely registered server name, like if people don't believe me, I can do resolve DNS, and then give it that. We have our name with garbage. Oops. Hey, we're back. I don't know whether that's a sign that I should get off the stage or something. I don't know. They're flashing the lights at me. Party's over, go home. Anyway, you can just probably see at the end that the IP address is actually 10.0.0.80, which is actually my Linux box. And so if we choose that instead and try and connect, and of course, give it the correct credentials, hopefully, takes a little bit of time, we should see traffic going through, and we've authenticated to our server, and we've basically spoofed the SPN through doing that operation. Okay. Now, of course, what you can do with that is open to debate, but anyway. So the final thing I want to talk about is the Kerberos ticket laundry. Now, I've already mentioned that one of the problems of a lot of this is if the client, for example, enables integrity checking or encryption, then certain services like LDAP will force that on you. And of course, if it forces it on you, then you can't relay your authentication traffic to those servers. And that's kind of a problem. And same with things like SMB and all that sort of stuff. They have very similar features. So I thought, well, is there at least a scenario where I can get potentially bad Kerberos relayable traffic and make it good again, launder it somehow between my client, my attacker box, and the actual target destination server? In certain limited scenarios, yes. So we have a client, and it's we convince it it's trying to connect to the laundry server somewhere. Now, crucially, the laundry server has unconstrained delegation enabled. And what this means is that as long as the authentication on the client specifies the delegation parameter, it will allow laundry to pretend to be the client user itself. So we relay the traffic from the client to laundry via evil host. Now, hopefully, what we need to find on laundry is some sort of service which doesn't care about the signing or encryption value of the authentication scheme, but crucially, will give us some sort of primitive to connect to, say, a file server over SMB, which would require it. And because once it gets to laundry, it can generate its own signing keys and all that sort of stuff, we can use that as a way of laundering those Kerberos tickets to our delegated authentication on file server. Now, you may think, this is so hypothetical. This is utter rubbish, right? You never find a service which implements this. So I did find a service which implements this. If you know what Petit Potam is, it's exactly the same service, the EFS RPC service. And crucially, in a standard domain environment, all domain controllers have unconstrained delegation enabled on them. So not only is EFS RPC enabled, not only does EFS RPC not require signing or encryption for your RPC protocol, it also allows you to connect to arbitrary SMB servers and write files to them. That's kind of a useful primitive. Unfortunately, they fixed that. But yeah, you can't have everything. If you don't want them to fix something, you don't tell them about it in the first place. So we'll just have a very quick demo of that. And it will also hopefully demonstrate something also separately interesting. So I have a network share somewhere on server 2022. And of course, if I relay to this, it's got signing and encryption turned on. I would not actually be able to relay Kerberos authentication to this because I wouldn't know the signing and encryption. However, an admirer has sent me a document. Fortunately, you can't read that very well. But they've sent me a document saying, hey, just open this Word document, can you? Because I really love you. So we open that document. Oh, it's a nice Valentine's Day card. It's designed for printing, of course, so it obviously not a major problem. But hopefully, we now have a file on our server. That's kind of weird. And the file has come from 10.0.0.80, which is my malicious man-in-the-middle box. And what that's doing is you can specify a HTTP URL for a Word document template file, and you can get it to do automatic Windows authentication to an arbitrary server on the local system, just by opening. And as you can see, there was no indication that that was happening behind the scenes, other than if you don't run the web server, it tends to hang a bit. They tend to notice at that point. That's kind of interesting. So to conclude, there's plenty of scope here if people want to go looking at what other protocols do. And I'm not saying that what I've found is necessarily the only way of exploiting that. Like WinINet, maybe there's a way of abusing that sort of DNS, like multi-DNS trick or something like that. Maybe there's a way through the code. There's a lot of complex code in there. RDP, I only really looked at it for that cheap demo that I just had. WinRM, Negotiate Stream. I also not really looked at non-Microsoft code, how they use it. I kind of looked a bit at Java, and I gave up after like reading various things about how to enable Kerberos in Java, and like it basically never worked, so I just gave up, as everyone should do with Java. But I've also not looked at interactions like how applicable is this to Linux machines with GSS API usage of Kerberos, for example? I don't know. So there are things some administrators can do. Of course, they can like disable things like link local name resolution, because that has all manner of bad, regardless of whether you could abuse Kerberos on it. Locking down your DNS server to prevent users modifying, adding new arbitrary records to it. Disabling Windows authentication endpoints, or if you're going to have them, turn on HTTPS with the extended protection for authentication. And also you can do things like disabling the CNAME DNS lookup in Chromium browsers. But fundamentally, much as I'd like to say that, oh, the world's falling down, Kerberos is just as broken as NTLM, fortunately, it's all shades of gray. Like, it's not quite as bad as NTLM. So disabling NTLM is still a useful thing in a Windows environment. So thanks to the various people who've inspired me on some of this research as I've been going through and doing tools, and thanks to OffensiveCon and the attendees here for having me, and it's been good to give my demonstrations to all of you. So thank you very much.